Okay, let's go. Number 1. The Zoo Hypothesis. The year is 1973. You're an astronomer at MIT's Haystack Observatory named John Ball, and you've just committed to paper the first sentence of a short academic paper you're about to submit to the journal Icarus. The sentence does not use dramatic language. It does not reach for effect. It states, in the flat register of scientific argument, that the most economical explanation for the observed silence of the cosmos is that we are being watched, and that the watching is deliberate. You pause before signing the submission. What you've written is either wrong or the most important thing anyone has written in the history of science. You submit it. The paper was called The Zoo Hypothesis. Ball's premise was stripped to its logic. The Fermi paradox, the observation that a universe this old and this large should be full of communicating civilizations, yet is completely silent, has many proposed solutions. Ball argued that one fit the data better than the others. Not that civilizations don't exist, not that they haven't survived, not that they lack the technology to contact us. The answer: they have found us, they are aware of us, and they have decided not to make contact. The model was precise. You don't transmit to the animals in a wildlife preserve. You observe. You document. You maintain conditions that allow natural development without external interference. Earth, in Ball's framework, is not an undiscovered planet in a quiet galaxy. It is a managed exhibit. The managers, by design, are silent. The logic forced an immediate and uncomfortable implication. If one civilization had decided on non-interference, that would not require universal silence. Other civilizations could still contact us. The fact that the sky remains quiet across every frequency we've monitored, across every direction, for as long as we've been listening, suggests the silence is not any single civilization's personal policy. It is coordinated, maintained by agreement. Enforced across the entire volume of space we can observe, Ball named this coordination mechanism the Galactic Club. The idea: spacefaring civilizations, once they achieve a certain threshold of development, are admitted to an interstellar community with agreed protocols. One protocol concerns developing civilizations. You don't disturb them. You observe. You wait. The criteria for admission for being upgraded from exhibit to peer, from object of study to fellow member, are not specified anywhere we can read. We have no record of what threshold earns contact or how close we are to it. Here's where it gets strange. Researchers working in the same framework after Ball's paper proposed that the non-interference might not be merely passive. Robert Freitas Jr. developed what he called the interdict scenario, the possibility that an advanced civilization maintains the quarantine not only through restraint, but through active management intercepting our broadcasts before they reach other star systems, filtering our electromagnetic signature from the interstellar medium. In this version, we aren't simply being ignored. We are being managed. Our transmissions are going out into space. We don't know whether they're reaching anyone, because someone may be making sure they don't. The Zoo hypothesis makes a specific prediction. As our detection capabilities improve, we should continue to find nothing. Every new telescope, every improved frequency range, every additional listening protocol should return the same result, because the silence is not a feature of an empty universe. It is a feature of a policy. That prediction has been consistent for 50 years of increasingly sensitive listening. The hypothesis has accumulated hundreds of citations in the serious academic literature on the Fermi paradox and remains an active proposed solution. The fence is holding. Whether what's on the other side is a research institution, a governing council, or something with no analog in our frameworks, the asymmetry is unchanged. They can hear us. We cannot hear them. That asymmetry, 50 years after Ball named it, has not closed by a single measurable degree. What would we have to do to cross the threshold? What are they waiting to see? Number 2. The Dark Forest Theory. The year is 2008. You're Liu Cixin, China's most widely read science fiction writer, and you're completing the second novel of a trilogy that will become the most translated Chinese work in history. The novel is called The Dark Forest. The theory at its center is not fiction. It is applied game theory, a set of logical premises drawn out to their inevitable conclusion about why the cosmos is silent. The conclusion: silence is the only strategy that keeps a civilization alive. The framework builds from 3 premises that are difficult to argue with. First, The universe contains finite resources. Second, life that survives long enough develops the capability and impulse to expand and consume those resources. Third, you cannot fully verify the intentions of another civilization, regardless of what signals they send, what agreements they offer, or what they appear to be. From those three premises, one conclusion follows with the compulsion of mathematics. If you detect another civilization, your optimal move is to destroy it before it can destroy you. The logic does not require malice. It requires only rationality operating across evolutionary time. A civilization that chooses compassion over preemptive elimination might be annihilated by one that doesn't. Over millions of years of competition in a finite universe, the only civilizations that survive to old age are the ones that learn to strike first, in silence, without announcement. The universe therefore fills with civilizations that hide and watch for others to reveal themselves. Every signal is a location. Every broadcast is a vulnerability. Every listening attempt is a risk. This argument extends beyond Lucikson's fiction. The underlying game-theoretic logic has been engaged by researchers working on the Fermi paradox as a coherent and internally consistent solution. The structure follows from first principles, resource competition, uncertainty about intent, asymmetric risk, and doesn't require any assumptions that aren't already embedded in our understanding of how competitive systems behave over long timescales. Whether civilizations would actually adopt this doctrine is debated. Whether the logic leads there if they do is not. Here's where it gets strange. We have been broadcasting for over a century. Commercial radio began in the early 1920s. Television followed. Our electromagnetic signature has been expanding outward at the speed of light at 186,000 miles per second since the early 20th century. The sphere of detectable transmission noise surrounding Earth is now roughly 100 light-years across, and it contains everything. The 1936 Berlin Olympics broadcast, the first moon landing in 1969, decades of radar pulses, military transmissions, and satellite signals. Every year, the sphere grows. Every year, the edge of it reaches star systems that have never heard from us before. In the dark forest framework, that expanding sphere is not a cultural achievement. It is an expanding trail of coordinates. Any civilization within that radius that has the technology to detect it knows where we are, what our language sounds like, and what our technological level has been at every year since the transmissions began. The question of whether any such civilization is listening is unanswerable right now. The question of whether they are deciding what to do is different. The dark forest theory offers no timeline. It makes no promise about what comes next. It simply states that the silence of the galaxy is not natural, it is maintained. The civilizations maintaining it are the ones that survived long enough to understand the alternative. They don't announce themselves. They watch. They wait for signals that expose location. They assess capability. They decide. We lit a fire a century ago. We have been broadcasting its location ever since. Number 3. Fast radio bursts. The year is 2007. You're Duncan Lorimer, radio astronomer at West Virginia University, and you're reviewing archival recordings from the Parkes Telescope in New South Wales, Australia. Data collected on July 24, 2001, during a survey of the Small Magellanic Cloud. Your colleague Maura McLaughlin flags something in the printout. A burst of radio energy lasting approximately 5 milliseconds. Not a gradual rise and fall. A sudden, narrow spike arriving and vanishing so fast the recording barely has time to register it. The dispersive sweep, the way different frequencies arrive at slightly different times after crossing a vast column of intergalactic electrons, indicates the burst traveled an enormous distance before reaching the telescope. Not from within our galaxy, from somewhere extragalactic. You calculate the energy. In 5 milliseconds, whatever produced it, released the equivalent of what our sun radiates in an entire day. The paper Lorimer published in Science in 2007 described what would become known as the Lorimer burst, the first fast radio burst, or FRB, ever identified. The community was skeptical. A single detection in archival data could be an instrumental artifact. Then other facilities found their own bursts, and skepticism became documentation. The sky is saturated with them. Hundreds have now been cataloged. Most fire once, from an indeterminate direction at extragalactic distances, and never repeat. Some do. FRB121102, detected at the Arecibo Observatory and confirmed as a repeating source by Laura Spittler's team in a paper published in Nature in 2016, was the first burst known to return. Its source is a dwarf galaxy approximately 3 billion light-years from Earth. FRB180916, detected by the CHIME telescope in British Columbia and published in Nature in 2020, repeats on a cycle of 16.35 days. Not approximately 16 days, not varying between 15 and 17. 16.35, cycling with a precision that exceeds what most proposed natural mechanisms comfortably explain. During each cycle, FRB180916 emits within a window of roughly 4 days and then goes quiet. Something out there is operating on a schedule. Here's where it gets strange. In 2017, Harvard astrophysicists Manasvi Lingam and Avi Loeb submitted a paper to the Astrophysical Journal Letters asking a precise question. If a sufficiently advanced civilization wanted to accelerate enormous spacecraft across interstellar distances using focused radio beams, a technology physically achievable in principle, what would the energy output look like? To a detector the beam briefly swept past? The numbers they calculated match the observed properties of fast radio bursts: burst duration, energy scale, dispersion characteristics, frequency structure, all consistent. The paper was not retracted. The argument has remained in the literature. The implication, if the hypothesis is correct, is this: no one is trying to contact us. A directed propulsion beam points at the spacecraft it is accelerating, not at Earth. We are not receiving a message. We are grazing the edge of an industrial process, operating at stellar energy scales, catching the fringe of a beam as the geometry briefly aligns. The way you might notice a lighthouse beam cross your window for a fraction of a second without the lighthouse having any awareness you exist. Every time an FRB lights up our detectors, we may be catching a momentary glimpse of a civilization's propulsion infrastructure. Whatever is operating, it has not noticed us. It is simply working at energies measured in what a star produces in a day, on a timetable precise enough to set a clock by, at distances so vast that its nearest activity may be billions of light-years from here. The burst with the 16.35-day cycle will return on schedule. Something is running on a timer we don't control, and it doesn't know we're listening. Number 4. Directed panspermia. The year is 1973. You're Francis Crick, co-discoverer of the structure of DNA, Nobel Prize laureate in physiology or medicine, and you're submitting a paper to the journal Icarus alongside biochemist Leslie Orgel. The paper does not reach for dramatic language. It lays out, in the flat register of scientific argument, the following proposition: life on Earth may not have originated here. It may have been sent. The argument begins with a problem that has not been resolved to general satisfaction. The fossil record shows that life appeared on Earth very rapidly after surface conditions allowed it within a few 100 million years of the planet cooling enough to permit liquid water. Given the complexity of even the simplest known self-replicating cell, the precise coordination of chemistry required, and the probability estimates for how long random molecular processes need to assemble such a system from scratch, several researchers have argued the timeline is too short. Crick was one of them. He concluded that the available time on Earth did not comfortably accommodate the probability of abiogenesis, the spontaneous origin of life from non-living chemistry occurring on this planet alone. A second observation sharpened the argument. The genetic code, the specific mapping between nucleotide triplets and amino acids that all known life on Earth uses, is essentially universal. Every bacterium, every plant, every animal operates on the same molecular language, with only minor variations at the margins. Either the code evolved once, in a common ancestor of all life, and was locked in before any lineage diverged, or it was established by a source that had already solved the chemistry problem elsewhere and delivered the solution here. Both explanations account for the universality equally. Only one accounts for the complexity arising faster than the probability models suggest it should have. Crick and Orgel proposed that an advanced civilization could have seeded Earth and potentially other worlds by launching microorganisms inside an unmanned spacecraft. Simple, durable organisms, selected for their resilience to interstellar transit, directed toward candidate planets identified by the sending civilization's astronomers. The spacecraft would not need to return. The organisms would not need to survive the journey intact as individuals. Bacterial spores can withstand conditions far outside the range any planet's surface provides. The seeding event, if it occurred, happened before any complex life existed here, and would leave no record we could distinguish from natural origin. Here's where it gets strange. Crick did not treat this as a speculative aside. He returned to the idea in a full-length book, Life Itself, Its Origin and Nature, published in 1981, where he examined the evidence more extensively and held to his position. The civilization he described as the potential source was not primitive. Any organization capable of synthesizing life, selecting organisms suitable for interstellar dispersal, engineering a delivery vehicle, and identifying habitable target worlds was already operating well beyond our current capabilities. They solved the biochemistry of life as an engineering problem. They knew where Earth was. They knew what they were planting. If they exist, they watched every step of what their project produced. The first self-replicating cells, the first photosynthesizers, the Cambrian explosion of complex animal forms, the sequence of mass extinctions and recoveries, the emergence, on a timeline any civilization that understood biology could anticipate in rough terms, of a species capable of examining its own DNA and eventually writing papers asking how life on this planet began. They have answers to that question. They have had them for longer than multicellular life has existed here. Number 5. The lurker hypothesis. The year is 1983. You're Robert Freitas, Jr., a researcher publishing in the Journal of the British Interplanetary Society, and you're making an argument that will reshape how a small number of very serious scientists think about SETI. The argument is this: the entire approach of listening for radio signals is based on an assumption that may be wrong. The assumption is that an advanced civilization would broadcast. Freitas argued they wouldn't. Broadcasting is inefficient. Signals expand in all directions, lose strength with the square of distance, take centuries to arrive, and require the receiver to be listening at exactly the right moment, on exactly the right frequency. A civilization advanced enough to be worth contacting would not broadcast into the void. It would send something physical, something that doesn't degrade with distance, something patient enough to wait, something that might already be here. The lurker hypothesis proposes that extraterrestrial civilizations may have deployed physical artifacts into stellar systems throughout the galaxy, including our own not probes passing through in transit, but probes parked in stable positions, placed to observe a developing world over extended periods without expending fuel or emitting signals that would reveal their presence. The ideal hiding spots are precise and calculable. The Earth-Sun Lagrange points gravitational equilibrium zones, where a small object can maintain stable orbit essentially indefinitely, are the most commonly cited candidates. L4 and L5, the zones that trail and lead Earth in its orbit by 60 degrees, are extraordinarily stable. An object placed there requires minimal energy to remain in position for billions of years. Crucially, L4 and L5 are each approximately 93 million miles from Earth, the same as the Earth-Sun distance, and both zones are already occupied by hundreds of thousands of natural rocky bodies called Trojan asteroids. That population is the key. A manufactured artifact the size of a desk, engineered by a civilization millions of years more advanced than us, would be indistinguishable from the natural bodies surrounding it, unless we applied specific instruments to look for the signatures of artificial construction. We have not. The catalogs of L4 and L5 objects exist for impact risk assessment purposes. That analysis does not require distinguishing natural rock from manufactured structure. The two tasks are different. The instruments optimized for one are not the instruments needed for the other. Here's where it gets strange. Researchers Haq Misra and Koparapu published a paper in Acta Astronautica in 2012, formally proposing SETA search for extraterrestrial artifacts as a discipline distinct from radio SETI. The paper argued that decades of listening had left the most direct alternative unexplored. The communication might already be physically present in our solar system, in a stable orbit, waiting. No mission has yet been designed specifically to search for manufactured artifacts at the Lagrange points, with instruments optimized for that purpose. The timeline is what makes this genuinely difficult to set aside. A probe placed in L4 before complex animal life evolved on Earth, placed 500 million years ago by a civilization that existed then, would still be in position now. It would have watched the first nervous systems form. It would have watched every mass extinction. It would have watched multicellular life radiate into the ecological niches the dinosaur extinction left behind. It would have watched the first anatomically modern humans. It is 93 million miles from Earth right now, in a population of rocks we have cataloged for safety reasons, recording everything. No one has looked. Not systematically. Not with the right instruments. Number 6. The Bracewell Sentinel. The year is 1960. You're Ronald Bracewell, radio astronomer at Stanford University, and you've just published a short letter in the journal Nature titled Communications from Superior Galactic Communities. The letter makes a technical argument. Nobody in the field has assembled quite this cleanly before. Radio signals are the wrong strategy for interstellar contact. They dissipate with the square of distance. They require a receiver to be pointed in exactly the right direction, at exactly the right frequency, at exactly the right moment. The probability of a successful detection across the distances and timescales involved is, Bracewell argued, small enough that any civilization serious about making contact would not rely on it. The better strategy is different. Send a messenger. Send it early. Have it wait. Bracewell's proposal was precise. Advanced civilizations would dispatch automated probes to stellar systems they identified as promising systems with sun-like stars and stable planetary zones. The probes would travel at a fraction of the speed of light and arrive long before the local civilization developed any detection capability. Once there, each probe would take up a stable orbit and enter low-power monitoring mode. It would be programmed to recognize the specific electromagnetic signature of a civilization crossing the radio technology threshold. When detected, the probe would respond. Contact would happen locally, in this solar system, with no centuries-long message delay. The emissary would already be here. The concept received immediate serious attention. Arthur C. Clarke had written his short story The Sentinel in 1948, more than a decade before Bracewell's letter imagining an artifact placed on Earth's moon, dormant for millions of years, programmed to trigger when the species above it reached sufficient capability to find it. Clarke expanded this into the screenplay for 2001, A Space Odyssey, in 1968. Bracewell probes became a standard entry in SETI theoretical frameworks, not a fringe proposal, not science fiction dressed as theory, but a recognized category of proposed interstellar communication strategy. What makes the concept distinctly disturbing is not the technology. It is the duration of the wait. Here's where it gets strange. A probe placed in this solar system before complex animal life existed on Earth would have been in position for more than 500 million years before the first nervous system appeared anywhere on this planet. It would have watched every mass extinction event. It would have watched mammals inherit the ecological space the asteroid cleared. By the time the first radio transmission left Earth, that probe would have been waiting for a duration so far beyond human comprehension that no analogy adequately captures it. It doesn't experience that wait. It simply runs its monitoring program, continuously, until the trigger condition is met. The trigger is unknown. Radio is the obvious threshold, and we crossed it over a century ago. Spaceflight is another crossed in 1957. The ability to detect planets around other stars and potentially identify inhabited worlds is a third capability we developed through the 1990s. The ability to characterize exoplanet atmospheres for biosignatures is a fourth something we are doing now with the James Webb Space Telescope. Any of these could be the threshold. We have crossed all of them. If the probe exists, and one of these was the trigger, it knows. We would not receive any indication of that until it decided to act on it. No dedicated search for Bracewell probes has been conducted. No mission has been specifically designed to look for manufactured objects in the Lagrange zones with artificial signal characteristics. If it is there, it is assessing. We don't know what conclusion it has reached about us. Number 7. The Berserker Hypothesis. The year is the late 1940s. Your mathematician, John von Neumann, working through a theoretical problem that begins as an abstract question about machinery and ends somewhere considerably more unsettling. The question is whether a machine can be constructed to replicate itself, to manufacture functional copies of itself from raw materials it gathers from its environment. Von Neumann demonstrated mathematically that such a machine was achievable in principle. It required three components: a universal constructor capable of assembling any specified design, a complete description of itself, and a control system to execute the construction sequence. All three were logically feasible. The machine was a thought experiment with real teeth. Applied to interstellar exploration, the implications were developed by researchers in subsequent decades into something with genuine range. A civilization that builds a single self-replicating interstellar probe and launches it toward the nearest star would, within a few million years, fill the galaxy. One probe arrives, harvests raw materials from the local asteroid belt, manufactures copies, launches them toward the next set of stars. Those copies replicate. The exponential spread saturates 400 billion star systems in a time frame that is, on cosmic scales, brief. This observation led some physicists, including Frank Tipler, to argue against the existence of extraterrestrial intelligence on exactly these grounds. If any civilization had ever existed long enough to build such probes, the probes would obviously be here already. Since they are obviously not here, the civilizations don't exist. The counter reading is quieter and less comfortable. What if the probes are not designed to be obvious? The berserker hypothesis proposes that self-replicating probes may be programmed not to make contact, but to eliminate. The survival logic follows from the same game-theoretic framework as the dark forest theory. A civilization facing competition in a finite universe might decide that the most reliable long-term strategy is to eliminate developing civilizations before they become threats. Program the probes to replicate and spread. Have them monitor each inhabited system they reach. When any system crosses a specified threshold of capability, the local probes respond not with a signal, with termination. Here's where it gets strange. The threshold is the central unknown in this scenario, and it is what makes the hypothesis genuinely difficult to dismiss. What capability level constitutes the trigger? Nuclear technology, which humanity first demonstrated in 1945. Radio transmission, which we developed in the early 20th century. Spaceflight, achieved in 1957. The ability to detect and characterize planets in other solar systems, which we began doing in the 1990s. We have crossed every one of these milestones. If any of them was the threshold, and if the response chain involves travel time or decision lag, the timeline may already be running in the background without our knowledge. The berserker model predicts exactly the observable universe we inhabit. Silent, apparently devoid of advanced civilizations, with no signals and no contact across any frequency we monitor. Not because life is rare, because every civilization that reached a certain capability was eliminated before it could expand and broadcast further. The silence is not the silence of absence. It is the silence of a galaxy that has been emptied, repeatedly, of anyone who announced themselves at the wrong moment. The probes don't need to announce themselves. They need only to watch, to wait, and to be patient. And patience, for a machine that doesn't experience time passing, is a structural property rather than a choice. They have been waiting for however long they have been waiting. They are still waiting. We don't know what we would have to do to become the next item on the list. Number 8. The Planetarium Hypothesis. The year is 2002. You're reading a book by British physicist and astronomer Stephen Webb titled, "If the Universe is Teeming with Aliens, Where is Everybody?" Webb is a careful thinker working through every serious proposed solution to the Fermi paradox, the documented observation that a universe this old and this large should be producing detectable signs of intelligent life, but isn't. He evaluates the proposals without dismissing any on grounds of discomfort. One, which he places late in the volume, is in a different category from the others. Webb calls it the Planetarium Hypothesis. The premise is this: the observable universe as we perceive and measure it is not the actual state of the universe. The signal reaching our instruments has been altered. We live inside a construction designed to appear empty. The Planetarium Hypothesis holds that a sufficiently advanced civilization, one that has had hundreds of millions or billions of years longer to develop than us, could, in principle, exercise control over the electromagnetic environment that separates us from the rest of the cosmos. Every photon we collect with our telescopes, every radio wave we detect, every gravitational wave our sensors measure, passes through the electromagnetic medium of space before reaching Earth. A civilization with the capability to manage that environment could render the universe as we observe it, rich in physical structure, accurate in its physical laws, full of stars and galaxies, and completely devoid of any signal that points to another living civilization, not because other life doesn't exist, because the signal revealing it has been removed before it arrives. The technology this requires is not presented as magical. It is an extrapolation of what we ourselves can do, projected forward across the gap in development between us and a civilization billions of years older. We generate photorealistic environments. We intercept and alter signals. We build systems that manage what information reaches a receiver. Apply those capabilities to a civilization that has been refining them across geological timescales, and a controlled electromagnetic environment is within the range of the conceivable, not demonstrated, but not excluded by anything we understand about physics. The purpose in Webb's formulation is paternalistic rather than hostile. A developing civilization, encountering evidence of a fully populated universe before it has the context to process that information, might be destabilized in ways that prevent its further development. The management is a form of quarantine similar in intent to the zoo hypothesis, but operating at a completely different architectural level. Not silence imposed on a real universe where others agree to stay quiet. The signal itself, altered. Here's where it gets strange. If the construction is perfect, no internal test can detect it. Every instrument we build to examine the cosmos operates within the managed environment. Every measurement we take returns data consistent with the constructed presentation. There is no experiment we can design that steps outside the theater to compare the managed view with the unmanaged reality, because every experiment uses instruments that receive the managed signal. This is not a philosophical thought experiment. It is a precise statement about the limits of verification from inside a closed system. The James Webb Space Telescope, launched in 2021, has returned images of galaxies from the universe's first few 100 million years that appear more massive and developed than current models of early cosmological structure formation predict. The anomalies have several candidate explanations: revised physics, incomplete models, observational effects not yet fully characterized. These will be examined methodically. The planetarium hypothesis is not on the candidate list, but it is not excluded by the data either. If the planetarium is running, we are the audience. The operators are outside the theater. They can see us watching the screen. We don't know if its doors open from the inside. Number 9. The simulation hypothesis. The year is 2003. You're Nick Bostrom, philosopher at Oxford University, and you've just completed a paper published in the journal Philosophical Quarterly under the title, "Are You Living in a Computer Simulation?" The argument is a trilemma, a set of 3 propositions, one of which must be true, with the math constructed to demonstrate no escape from the 3 options. First branch. Nearly all civilizations at our level of technological development go extinct before reaching the capability to run detailed, high-fidelity simulations of conscious minds. Second branch. Civilizations that reach that capability choose not to run such simulations. Third branch. We are almost certainly living inside a computer simulation right now. The mathematics behind the third branch are straightforward. A civilization capable of running detailed simulations of conscious minds would quickly generate enormous numbers of them. The computational cost per simulated mind decreases as the technology improves. The number of simultaneous instances expands exponentially with processing power. If we assume any non-trivial fraction of advanced civilizations choose to run what Bostrom calls ancestor simulations, reconstructions of their own earlier histories, the simulated minds they produce vastly outnumber any biological originals. If you are a conscious being, statistics say you are far more likely to be one of the countless simulated instances than one of the rare biological originals from base reality. The probability of being in base reality, if the third branch is correct, approaches 0. Bostrom's paper was not received as fringe. Cosmologist Max Tegmark at MIT has engaged with the argument as a coherent framework. At a 2016 symposium at the American Museum of Natural History, Neil deGrasse Tyson said he found the case for simulation very compelling. The argument has been taken up seriously in philosophy, physics, and computer science because the logic is technically sound, not because of cultural enthusiasm. If the premises are granted, the conclusion follows. The key question for this context is not whether the simulation hypothesis is true. The question is what it implies about who is running the simulation. If we are inside one, someone has direct computational access to everything occurring within it, not access through telescopes or sensors. Access through the code itself. Every particle interaction, every quantum state, every thought, every moment of every life inside the simulation is visible to the operators as a matter of the system's architecture. They are not watching from a distance. They are watching from a level that encompasses the entirety of our physics. Here's where it gets strange. Our universe's physical laws carry features that some researchers find suggestive, though the interpretation is genuinely contested. The fundamental constants, the strength of gravity, the charge of the electron, the cosmological constant, sit in an extraordinarily narrow range that permits matter, stars, chemistry, and ultimately conscious observers to exist. If those constants were slightly different in almost any direction, the universe would be inert, no atoms, no stars, no complexity of any kind. This fine-tuning is typically explained by the anthropic principle. We can only observe a universe compatible with our existence. But fine-tuned parameters are also precisely what you would expect from a simulation designed to produce specific outcomes. You set the values to produce the result you intend. The two explanations, anthropic selection and deliberate design, produce identical observational predictions, which means the data cannot distinguish between them. If the simulation hypothesis is correct, the Fermi paradox dissolves entirely. There are no other civilizations, because the simulation renders only one. The operators did not build a populated galaxy. They built a backdrop of stars and physical laws, and one inhabited world, real in every testable way, whose instruments would search the empty backdrop and find nothing. Every signal we look for, and do not find, is exactly what they put there for us to receive. Number 10. The Kardashev Type 3. The year is 1964. You're Nikolai Kardashev, radio astronomer at the Sternberg Astronomical Institute in Moscow, and you've just completed a paper being submitted to Soviet astronomy under the title Transmission of Information by Extraterrestrial Civilizations. The paper addresses a technical question about signal power. If another civilization were transmitting toward us, what energy level would they need to operate at for the signal to be detectable across interstellar distances? To answer it, Kardashev first has to answer a prior question: what energy levels are physically possible for a civilization at different stages of development? He constructs a scale. Type 1. Total mastery of a planet's energy resources. Type 2. Total mastery of a star's energy output. Type 3. Total mastery of an entire galaxy's energy output. He calculates the corresponding transmitter power for each category. Then he notes something the paper does not dwell on, but which has compounded in implications ever since. The Milky Way is old enough that a Type 3 civilization could already exist here. The galaxy is approximately 13.5 billion years old. The first stars formed within the first billion years. A civilization that emerged 5 billion years ago before our solar system had condensed from gas and dust, and that expanded at even a fraction of the speed of light, could have reached every star system in the Milky Way long before Earth existed. Carl Sagan later refined Kardashev's scale with decimal values, placing Earth at approximately type 0.73, still mastering the fossil energy of a single planet, far below type 1. A type 3 entity would operate at a scale so far above ours that the gap between us and them is greater than the gap between us and a bacterium. In 2015, astronomer Roger Griffith, working with Jason Wright and a team at Penn State University, published what they called the G-HAT survey in the Astrophysical Journal supplement series Glimpsing Heat from Alien Technologies. Using data from NASA's WISE infrared space telescope, they examined 100,000 galaxies for anomalous mid-infrared signatures. The reasoning: a civilization harvesting energy at galactic scale would produce enormous waste heat, detectable as excess infrared emission beyond what normal stellar populations generate. The survey identified approximately 50 galaxies with mid-infrared excess that existing models don't fully account for. Natural explanations, starburst activity, active galactic nuclei, dust emission remain the preferred interpretation. None was definitively established for all 50 candidates. The survey was presented as an open result. Here's where it gets strange. A Kardashev Type 3 entity embedded in our galaxy would not resemble anything we think of as a civilization. After billions of years of operation and expansion, it would have become part of the large-scale structure we observe. Its infrastructure would be distributed across hundreds of billions of star systems. Its communications would be invisible to us. We have not demonstrated the ability to distinguish deliberate signals from natural phenomena at that scale. Its waste heat would look like interstellar dust. Its engineering projects would look like nebulae. If it chose to remain undetected by a young civilization like ours, it would not need to try. It would simply operate normally. We would see what we have always seen, a galaxy full of beautiful, apparently natural structures. If such a civilization exists in the Milky Way, it has known about Earth since before complex animal life evolved on this planet. It has watched every mass extinction, every evolutionary radiation, every step in the sequence that produced us. The silence it maintains toward us is not the silence of absence. It is the considered silence of something watching from so far above our position that the question of whether to make contact carries no urgency. It has been waiting long enough to wait longer. From the zoo hypothesis to the Kardashev scale, from the probes in our Lagrange points to the simulation running our physics, the same question repeats across every scale. The silence around Earth may be a managed condition, and whatever is managing it has been patient for far longer than we have existed to notice. Subscribe if you want to keep looking. Comment with which theory you find most convincing, and tell us where you're watching from.